Okay, so I'll just continue where Scott left off. Okay, so the last thing that Scott did is he gave you this example of homogenization of a periodic shear flow, right? So let's just recall, so the notation was that if you take the stream function right, so this A is nothing but the Lipschitz norm of this. That's what the meaning of A is the Lipschitz norm. Epsilon is the scale of oscillation, okay? And it's a scalar because we're in 2D, and so the associated velocity field is just grad perp. And what Scott showed at the end of the lecture is that if you take the drift diffusion equation with this drift, so if you take this operator if you take this operator, it homogenizes to a different operator as you zoom out, and that new operator, so this is zoom out, and the process is homogenization. You get a new operator, which is dt minus a different matrix, divergence of A bar grad. And what Scott also did is that he rewrote this in a smarter way, which is minus divergence of this matrix kappa minus psi A epsilon grad. Okay. So basically this oscillating matrix, this is a diffusion matrix, which is highly oscillatory, becomes this constant diffusion matrix. And A bar was, so the old matrix, and you get enhancement in the 1-1 component because this only points in the E1, right? So U A epsilon is parallel to E1. And so here you get enhancement, and the enhancement was some explicit thing. Okay.
How can we understand that in the first example of Scott, the velocity field was of amplitude 1, whereas that one is much smaller amplitude epsilon?
Who is of order epsilon here?
The velocity field U A epsilon.
It's of size A times epsilon.
Yes.
Because when you take a grad perp, this becomes A times epsilon.
I know.
Yes.
But the one of the first example of Scott was of amplitude 1.
Yes.
So how come so now the velocity field is much, the amplitude is much smaller, but oscillatory crazy, that I understand. How come that, because of the velocity field is much smaller in amplitude, how come it will lead to an enhancement of the diffusivity, which is a priori a bit surprising?
Well, you get enhancement. What Scott showed at the end of last lecture, that the amount of enhancement, so that if you look at the symmetric part of the, so you take the homogenized matrix, and you look at this at its action on any kind of vector. So this is just measuring the symmetric part, right? Yeah. So what Scott showed is that this is kappa, which is what you got for this, plus the average of the energy of the correctors. Right? So times kappa, right? Times kappa. So whenever the corrector is not equal to 0, or let me rephrase, the correctors were 0 mean, right? So I don't have to worry about constants, right? So whenever the correctors are not 0, also known as constants of 0 mean, this always enhances because it's a positive number. Always. And this has to do, of course, with the fact that this is divergence free. Yeah.
Maybe a physical statement would be, in the cell problem, if you set the diffusivity to 0, the particle doesn't go anywhere, it just goes around in a circle. If you set the diffusivity to 0 in this problem, the particle goes ballistic, so its effective diffusivity is infinite. So it only has a finite diffusivity because it actually cross-diffuses a little bit and stops flying away. So it's really frustrated ballistic dynamics here, which is why it can be so weak and such a huge diffusivity, which goes 1 over.
Essentially, just to follow up, in a shear flow, we're taking a shear flow in a channel like that, but in this direction, we're doing it periodic, right? So essentially, trajectories can achieve infinite length in principle as time goes to infinity. But in a cellular flow, they only travel finite distance. So this has access to infinite distances, whereas in a cellular flow, it doesn't have access to that. Its distance is always finite when kappa is 0. And this infinity you see, because if you send kappa to 0 here, you get infinity, right? But I don't know if this actually answered your question, because your question was about how come a small vector field still can cause enhancement.
Yes, more than 1 of order 1.
Okay, so it's not that it's more of the 1 of order 1, because it's more having to do with the fact that it's a shear flow versus a cellular flow. Because shear flow has access to these infinitely long trajectories as time goes to infinity, whereas the cellular flow has only access to trajectories that remain in a single cell for all time.
And I think it's also confusing because when I did the cell example, I had epsilon equal to 1, and I zoomed out to like infinity, and here we have epsilon equals small, and we're sort of at scale 1 isn't that. So I'm changing what is a microscopic scale.
Yeah.
I'm just changing the scaling all the time.
So Scott had epsilon equals 1 in his example, and he also had a is equal to 1. So in Scott's examples, both a and epsilon are 1, but there's still, even if you take them both 1, you see here you get a 1 over kappa, and before you got root kappa. It's really different.
Thank you.
Okay, so this was this formal computation that, of course, as was said at the end, was essentially done by G.I. Taylor. But there is a little caveat in this computation, which is how far do you need to zoom out to see it, right? Because the cellular flow oscillating at scale epsilon right? So if this is epsilon and these are shears like that, of course, how far do you need to zoom out to see this new operator? And if you don't quantify that statement, it's a useless statement because you see classical homogenization statements, and Scott already said this, I'm just repeating it, basically say assume scale separation goes to infinity, right? You have unit scale and epsilon and you're sending epsilon to 0. Or you have unit scale and scale r and you send r to infinity. There's nothing which is infinity here. In our construction, the ratio of two scales is going to be some number. So you need us to find a very quantitative way to say this when you zoom out. Okay? And the answer to this is that you need to zoom out at time scales which are much larger than the characteristic time scale of this vector field. Now, what is the characteristic time scale of a vector field? And of course, it's the CFL time scale. It's 1 over the Lipschitz norm. Okay, that's the characteristic length scale that you can associate to any kind of vector field. 1 over the Lipschitz norm. So here the Lipschitz norm is A, right? Because if you take another gradient of here, which is what you need to compute the Lipschitz norm, when you take two gradients of psi, the two gradients, the two epsilons cancel and you get A, right? So the characteristic time scale is A inverse, right? So you need to zoom out at time scales which are much larger than A inverse. But okay, much larger, what does that mean, okay? And the answer is this number appearing here also appears here. And so this is now a universal constant here, and here you write this object which doesn't have units. You see, A is a Lipschitz norm, so it has units of we said A inverse is a time, so it's 1 over time. Length scale over time is exactly the same length scale as a diffusivity, so this is a unitless number. And this is the amplification factor. And you also need to zoom out at space scales, which are much bigger than the characteristic space scale of U, which is what? Well, the characteristic scale is epsilon, right? Times the same number. So I keep writing this 1 here, but in the actual example that we're going to look at, this is always bigger than 1, so I don't have to write it. But in general, you write it, because I haven't yet chosen A, okay? So now, this is a little lemma you can prove now, okay? That if you zoom out on parabolic cylinders, in which the time length of the cylinder is a dimensional constant times that, and the scale of the cylinder, okay, in space, it has to be an ellipsoid, because these are not isotropic here. So it's an ellipsoid with lengths corresponding to this, right? One with the 1 and one with this. On that parabolic cylinder, which is big enough, you're going to see that the solution of this equation is very well approximated by a solution of this equation. That's the statement. Okay. So this is just recap of what Scott did, essentially, at the very end. So this is not news. Okay, so now construction of the vector field attempt 1. So again, Scott already said it in his lecture. What you would like is to replicate that image in somehow an iterative, like a fractal way, so that when you zoom out, you keep seeing that image. So you need to start somewhere. And where you need to start is at the smallest length scale available in your solution. And for diffusivity kappa in a continuous vector field, that's basically kappa, okay? So you start at length scale kappa. Kappa doesn't have units of length, but you know what I mean. So a unit of length is proportional to kappa. And then you zoom out once, somehow, in this way, you should see a new kappa at a different length scale. You zoom out once again, you should see a new kappa, and so on. So let me try to draw a picture. So if this is scale, okay, there is the 0 length scale, but there is no such thing because kappa is positive. Anything below scale kappa is erased by the diffusion, okay? Kappa. And if you now imagine that you have a sequence of numbers that go to 0. Okay? Take a sequence of numbers that goes to 0. These are length scales. So let's put them on this axis. So this is the size of the box, 1. The next smallest length scale is epsilon 1, epsilon m minus 1, epsilon m. And remember in the statement of the theorem, we said that we're sending kappa to 0 along a specially designed set. So what we would like is that this kappa is proportional to one of these epsilons that you've chosen. Okay, so this is within a factor of 2 of some epsilon capital M, for some capital M, which depends on kappa, of course. So you first pick this sequence, and then you say, okay, what is my molecular diffusivity? It's somewhere along this sequence. And let's assume that it's within a factor of 2 of one of the length scales, okay? So then what you would like to do is perform, okay, so this is the scale, and now effective diffusivity at that scale. And the effective diffusivity here is kappa. But after one iteration, it should become something else, right? So if you believe this picture, if your diffusivity here is kappa m, then the recursion says that kappa m minus 1 is equal to kappa m plus 1/2 kappa m times am epsilon m squared over kappa m squared. And then you keep going. Okay, this is just an heuristic. This is not a proof of anything, right? It's just an heuristic. So you somehow iterate this map, but you initiate it down here. And then you keep solving these recursions backwards, and hence, in the abstract, backwards cascade of effective diffusivities. And you hope that by the time you reach the size of the box, so this is kappa 1, or kappa 0, sorry, you hope that no matter where you started, kappa 0 is of order 1. That's the hope. So the hope is that kappa 0 is of size 1 independently of what little kappa was.
Do you hope or do you have conditions?
No, I mean, I'm just trying to say how we thought of the construction. This was a hope initially. Then you turn it into a proof. So this is a statement. It's proof, but initially you just hope that it's true until you can actually prove it. And you see the number of steps. Okay, what if the sequence was dyadic, 2 to the minus m, right? In that case, the number of steps you would need to do this would be log of 1 over kappa. So as kappa goes to 0, the number of such arrows would go to infinity. And this has a hope, basically, to get you from 0 to 1 in infinitely many steps, right? So this is consistent. Okay, so now let's actually write down a construction. So associated to the sequence of scales that goes to 0, which so far I have not chosen, let's associate a sequence of Lipschitz norms. So 1 is A0. And why are we doing that? Because we would like every single object, every single stream function with am epsilon m of x, which is am, and then some base, let's say right sign, but you'll see in a second that's not exactly what I mean. Let me write just x, okay? And let me write this as capital psi of x over epsilon m, and capital psi could be sine of 2 pi x2. It could also be 2 pi x1, okay? You would like these objects to have a C alpha norm of order unity independent of m. And again, the semi-norm in C alpha just says, look at psi of x minus psi of y, divide by x minus y to the alpha, take the supremum over all x and y, okay? And when is this possible? Well, no, you want the vector field to be C alpha, so this is C1 alpha. You want u to be C alpha, not psi. U is grad perp, so it should be C1 alpha. And this is possible if and only if somehow am, sorry, this is order 1, equivalent to am is epsilon m to the alpha minus 1. Okay? So now, by picking this sequence, you've frozen this sequence by that relation. So this is not a free sequence anymore. So this one was a choice, and this becomes something. Now, due to experience with other kind of constructions of wild solutions in PDEs, we somehow knew a priori that it would be, at least at the beginning, it would be convenient to have the sequence go to 0 slightly faster than geometric, okay? So if you let this first drop let's call it some number. Okay, so this is a parameter that you choose at the end of the proof. Make it some huge parameter. This defines epsilon 1. And then for all m larger than 2, define epsilon m. Okay, so you see, this is 2 pi periodic if epsilon m is 1 over an integer. And let me not write floors and ceilings, okay? But they should be integers. And so this squiggly means floor or ceiling. I'm too lazy to write down which one it is. Epsilon m minus 1 to the q, where q is strictly larger than 1. But it's going to be super close to 1. So 0 less than q minus 1, super small. And how small is chosen as part of the proof. This is a small parameter entering in the proof. Q minus 1 is a small parameter. And capital lambda is a large parameter. And at some point, you have to choose them. Yeah.
Explain again the idea. So capital M, it's not going to work for any vector field that I'll give.
No, in particular, given that I've written attempt 1, it's not going to work for what I'm about to write.
So epsilon capital M is my initial vector field, which needs to...
Yes, it's the scale of the most fine vector field that you care about.
But can I think about it as this?
Yes. Yes.
The initial condition for your series or the last condition for your series?
Yes, you can think about it like that.
So what does it need to satisfy that it's, I just don't see the capital M there or for any little.
This is so far defined for every little m in n. Okay.
I'm trying to understand if it's sensitive to your initial condition, is it sensitive
No.
to the procedure of how you choose which sequence did you choose?
You see this recursion here? Kappa m goes to this kappa m minus 1. In that sense, it is sensitive. How, like which number bigger of order 1 you get is sensitive to it. Did you choose am to be that or twice that? But the order, that it's order 1, it's not sensitive to anything, okay? And by the way, I mean, sine, we gave examples with sine. Sine is a particular function of 0 mean and whose mean of the square is a half. Pick any other function of 0 mean and whose square of the mean is a half, and you're going to get the same answers. So it's not really sensitive to that either. Okay, so now the only thing I've done now is I've defined these guys, and I've defined these guys. Let me now define the vector field, attempt 1 at least. How should I do this? I'll go here. So we're going to define the stream function recursively, okay? So the base stream function is 0. And then for all m greater than 1, recursively defined phi m of tx minus phi m minus 1 of tx. So these are stream functions. So I'm telling you what the stream function increment is, okay? And then you just add them up. So in attempt 1, this would be a sum over all k in z of what? So Scott already said this. If you take sine of 2 pi x2, it points in one direction. And so you get a very not eccentric, but a non-symmetric, no, it is also symmetric. It's anisotropic matrix. So if you want to get an isotropic matrix, you should also do sine 2 pi x1, right? So you need to oscillate them. So this k does exactly that. It oscillates directions. So let me define capital psi sub k of x, no scales, okay? To be sine 2 pi x1 if k is 1 mod 4, sine 2 pi x2 if k is 3 mod 4, and 0 if k is 0 mod 2. Okay? So this oscillates them, but it also leaves a little bit of, so you do a shear, then you do nothing, then you do the other shear, then you do nothing, you do the other shear, you do nothing, okay? So now these are shears which are pointing in different directions, so you need to glue them somehow. Okay, so you glue them. How do you glue them? With a partition of unity in time. So we're gonna do zeta of t over some time scale minus k, and now exactly am squared, am epsilon m squared, this guy of x over epsilon m. So I need to tell you what this zeta is. This zeta is a partition of unity. So zeta is a bump function, is a positive bump function, and its shifts do a partition of unity. So what do I want to say? I want to say that sum over k in z of zeta of x minus k is 1 for all x. That's a partition of unity. They're positive, okay? They only talk to their neighbors, okay? So you can have 1 minus a third, less or equal zeta, less or equal 1 minus 2/3. So it's a nice partition of unity. And you notice there's a new parameter tau m, which I didn't talk at all about. And this is the time scale at which you glue these shear flows. So it's a new object in the construction. Tau m is a time scale to be determined. Because remember, we fixed what the epsilons are, we fixed what the a's are, but these taus, we don't know yet what they are. We just put them there, okay? So now, what is the story on that board teaching us? It teaches us that if you want to do one step in the homogenization procedure, so this is one step of homogenization, the board on top, specifically this, says that you can only do that if there's enough room.
But I'm mystified by all the French holidays you put in there. Why is there the 0 when nothing happens?
Because it'll be huge pain if you have half a shear.
Okay, partitions of unity have the property that two neighbors talk to each other, but another second neighbor doesn't see this, right? I just don't want two shear flows to live at the same time. So I want one shear flow to talk to 0. Okay, I don't want one shear flow to talk to another shear flow.
So there is a flow at all times, it's just the way it's constructed.
Yeah.
There's a gap.
There's definite, that is a C infinity function of space and time.
Right.
For every fixed m, it's a C infinity function of space and time, and the limiting phi is the limit as m goes to infinity of phi m, and u is grad perp of phi is the limit m goes to infinity of um of grad perp phi m. Okay, in what sense is that limit? This limit is a strong limit in the sense of C alpha functions. This is a strong limit in the sense of C1 alpha functions, okay? But you define them recursively. And for every frozen m, you're C infinity. Just that when you send m to infinity, you're not, okay? So, but where I was saying that you need to have enough space. You see, you need to have enough space in space first. That's a strange statement to make. In scales. Thank you, Scott. I'm obviously not a native speaker. So you need epsilon m minus 1, which is the larger scale. So this is the larger scale to be much bigger than the old scale times this, right? So you need epsilon m minus 1 to be much bigger than the old scale times the amplification factor. You also need to have enough space in time. Okay, so the second condition says that this time scale must be bigger than this. What is the time scale that I'm talking about? The only time scale that's now introduced in the problem are those tau m's, right? So what you need is that tau m is bigger than the previous time scale. What does that mean? As I said, it's a Lipschitz norm, 1 over a Lipschitz norm. I've already written this there. I'm just going slowly over it. So, the moral of this little story here is that pick your epsilons, automatically get your a's with this relation, and now you have kappa given by this recursion, and if in addition you satisfy these things for all m, then you have a hope for the proof to work, okay? Okay, so first of all, you should say, wait, can't you just solve this recursion? And the answer is yes, of course you can. And what you will get, and this will matter at some point a bit later, so if you just solve this recursion, you're basically saying what power law is kappa, right? And it turns out that kappa m is a specific power law, 1 minus alpha minus a new parameter, unfortunately. And this new parameter is there because we don't have geometric scales. We have super geometric scales. So this gamma is related to how far we are from geometric. It's just a number, but the point is that when q goes to 1, this number disappears. So if you want, ignore it, okay? If you want, ignore this. Okay. At this point, it's anything less than 1, right? I didn't say anything about what it has to be, just anything less than 1. Okay, so with this, given that you can solve this, you can simplify these expressions a little bit, right?
Is that 1 plus alpha? It should be 4/3. This is the reduction 4/3.
Yes, of course, Scott. I'm just... Yeah, when alpha is a third, you should get 4/3. Because that's the correct eddy diffusivity at scale epsilon. But okay. Now you can actually solve these recursions. And you can just compute what this is. Meaning I can plug this formula in there. And I can plug this formula in there. Okay? And what will I get here? Well, here I'm just going to simplify. And here I'm also just going to simplify for the moment. So I have not done what I just said I'm going to do. If you now want, you can plug that in there, okay? And I told you this from the beginning. This will always be bigger than 1. That's all I did here, okay? Okay, so now what is the strategy? So the strategy is to make that picture with going up the scales rigorous. So let's attempt to do that. Okay. So basically the preparation step all the parameters are chosen now, right? Including tau, who you just take to be this, okay? Times a large constant. Okay, preparation, you need to erase the absolutely smallest features in the solution. So I started the discussion on the top board by saying that there's nothing below scale kappa, right? So I need to do that. So the preparation is that pick capital M such that your molecular diffusivity is of size kappa capital M, which we just have agreed is of this size. Okay? And now, solve a different equation. Solve dt theta capital M minus kappa, which is also kappa M. But instead of putting the full velocity here, I erase all the scales below M. Okay, so you just put UM with the same initial data. And you're asking yourself, is this related to your original problem? So the only difference is that this has the full vector field, which is rough. This has a different vector field, which is C infinity smooth. It's just erased all the scales, and the answer is yes, they are very much related. In particular, you can prove a simple estimate of, I think I need to push this a little bit higher. And the simple estimate is that theta, this guy, minus the true solution in L infinity in time, L2 in space, plus the amount of diffusion they each experience, squared. So this is L2 in space and time. I would like to say that this is small, but I'm not going to say that it's small. I'm just going to say that it's within 90% of this. Okay? So this is going to be less than 1 over kappa over 10 times the thing you're after. Okay, so this is an estimate you can prove. And this is the estimate which says I erased all the scales that didn't matter. So up to making a 10% error, you can approximate the thing you're truly after, which is kappa times gradient theta kappa. You can approximate it with kappa gradient theta M. Okay? Because you're just making a 90% error. Okay, so all I'm saying is this, that kappa this is space-time. Okay, that's the consequence of this. How do you prove this estimate? Subtract the two equations, do a standard energy estimate. Nothing special. Okay? Okay, so you're done with the preparation step. So now you want to do the iteration step where you, yes?
Finish your sentence. So what is the interpretation of the time scale power? Is it
So far it has absolutely no meaning, but okay, so I should say something. This tau m, it is truly necessary only in 2D. Because in 2D, you know, we need to shear like this, shear like the other way, and we don't want them to talk to each other, right? What if you're in 3D? Well, then Scott already said it. I mean, you can just take pipes which shear in different directions, and in 3D, they don't talk to each other. And so you don't even need this tau m. But in this construction, the meaning of tau m, it's the scale at which you flip the shear left and right. Does this have a meaning? I don't know. Okay?
It's not the characteristic time scale of the eddies?
No, it's not. It's not. Okay?
Because I would not be happy at that scale.
Exactly. You should not be happy. Okay. So now you've done the preparation, and now you want to do, on the top board, you want to jump across the scales, right? So for all integers define theta little m as the solution of this equation, in which you replace the full vector field only by the vector field after m iterations. So you keep erasing features from the vector field. But you keep the same data. Okay? So in particular, theta capital M is exactly this one, because kappa capital M is exactly your old kappa. Okay? Define these objects. So now, what do you do with them? Let me go here. You want to prove the hardest part of the proof, which is the main estimate. By the way, this kappa M is this one, right? It's not some arbitrary thing. It's that one, obtained from the recursion. So these are obtained recursively as kappa m minus 1 is kappa m plus 1/2 kappa m times am epsilon m squared over kappa m squared. Okay, so the main estimate says the equation at level little m homogenizes to the equation at level m minus 1. Because if you can do this, you can keep going until level 0. Now, what does this actually mean? And it's embarrassing to talk about this in terms of Scott because I know nothing about the subject and he knows everything. So one of the things that it could mean is that the amount of diffusion, in total diffusion experienced at little m level is comparable to the total amount of diffusion at little m minus 1 level. So what does that mean? There exists a small parameter delta positive. By the way, delta is capital O of q minus 1 squared. So it's much smaller than this gamma there, such that kappa m gradient theta m squared divided by kappa m minus 1 this is close to 1. So what does that mean? You cut 1, you put absolute values, and you're saying this is small. How small? These have the same units, so this also doesn't have units. You should not put something like this. So here you put a constant, which is universal, and here you put epsilon m minus 1 to the delta, and this c has the units of epsilon to the delta, okay? But so this is small, and delta is positive, okay? Now, you prove more than this in the end, but I don't think it's worth writing the other things for this specific talk. But you do need to prove more. You can't just prove this, okay? Now, what if for some reason you can prove this estimate? Assume one can prove whoa. And by the fact that I've written attempt 1, of course the answer is no, you cannot prove it. Okay? But let's say you could prove it. Okay? What would be the consequence of that? Well, the consequence of that would be that you can just telescope an inequality of the same kind. So by telescoping, scope the bound star, you should be able to prove that kappa m gradient theta m L2 squared has upper and lower bounds. What are the upper and lower bounds? Well, in every step you make an error. From above, the error is 1 plus constant epsilon m minus 1 to the delta. Every time you make this error, so the errors accumulate. So you need to do a product here. Yeah. to capital M times something times, do we do it with initial data? Yeah. Just a second. No. Times kappa 1 gradient theta 1 L2 squared. And from below, you have the same thing, but with minus. Okay. Now it's very convenient. This is the place where it's very convenient to have super geometric things, because that product is finite. So this product is bounded from below and above.
That would be the same even if it were geometric. Right?
Sorry?
That would be the same if it were geometric, I guess.
I think there's a log issue then, but maybe not.
I think if you take the logarithm of that, you just do a series.
Okay. So what you have just shown now, at the end of this, combine this with this, and you have just shown that the true object you are after is less or equal 11 over 10 times 4 over 3 times kappa 1 gradient theta 1, and then 9 over 10 times 3 over 4 times kappa 1. So the last step is to just compute this, which appears on both sides. But that's easy now, because look at the equation it solves. It solves this with 1, right? And what is kappa 1? Well, kappa 1 is obtained by doing that recursion, and we have a formula here. Kappa 1 is epsilon 1. It's independent of little kappa. It's a number. It's independent of anything. So basically, you're proving that the total energy or variance or intensity dissipation rate of the true solution is bounded from above and below by the intensity dissipation rates for theta 1, but theta 1 has diffusion, which is order 1, no matter what kappa is. So, okay, that's a simple exercise now. The last step, and it's just a consequence of the Poincare inequality. So the last step should be that the solution of this equation you can just quickly prove that it has unit energy dissipation rate bounded from below by some kind of universal constant times kappa 1, the initial data. And there you go, that's the anomalous diffusion. No matter what little kappa was, you have a lower bound on this object by an object which is independent of kappa, right? So by going up the scales, these quote-unquote log many times, you've done infinitely many renormalizations in the sense of this increased or effective eddy diffusivity, and you have proven what you wanted. But of course, all of this is dependent on this statement. Okay? So how many minutes do I have? A lot? Oh, perfect, because I have a lot.
We are making a calculation, right?
Is it independent of kappa?
45 until 5, so you have 25 minutes.
Excellent. Thank you.
So just, I trust you guys, but so by curiosity, so did you say how you were choosing epsilon small m as a function of capital N? Did you say it somewhere? Or?
Yeah, so you see on the very top board, I said that epsilon 1 was capital lambda inverse. That's just a small number. You pick it. Maybe it's 1 over 10 to the minus 50. So maybe this is completely irrelevant for anything. So you pick a small number, and then recursively keep doing this. So epsilon 1 is this, epsilon 2 is lambda to the minus q, epsilon 3, you know what I mean, right? So they're chosen.
It's surprising to me that the product, the m, capital M times of something that doesn't depend on capital M should be finite.
But it does depend on capital M.
It's close to 1. You're multiplying much numbers that are very close to 1.
So
Logarithm of that.
in this product, every single number is super close to 1. So if this is not here, the product is 1. So now the error you make in every step from being 1 is incredibly small. So like Scott says, take the log, this becomes a sum. Log of 1 minus c times this is c minus this. And this is summable. So what you were really using, and you're correct, Scott, about geometric, thank you. Scott was, of course, correct. This works also if it's geometric, because that's the definition. Yes, thank you. So that's what we're using there, okay? So now, can we prove star? The thing I've just erased said that this Taylor diffusion works if you're modifying the heat equation with a zero mean shear flow, and in the case we've done also a periodic shear flow, okay? Now, are we in that situation? So we are at level little m, and we're asking, is this 2 pi epsilon m to the d periodic and zero mean? Well, by construction, this, so yes, for this, for the increment. That's how we designed the increment. We designed the increment to be periodic at that scale of zero mean. That was by design. So if you want this to be true there, you need to ask, and the answer is no. Why? So this increment oscillates at scale epsilon m. The old flow oscillates at scale epsilon m minus 1, which is much larger. So from the perspective of this increment, this looks like a constant, right? And so this induces in each 2 pi epsilon m to the d periodic cell, it induces a mean flow, mean background flow, which is essentially a constant. And by constant, I just mean it's a constant plus epsilon m divided by epsilon m minus 1. So plus a small number, okay? What's the size of that constant? Well, again, if you look at this object and you average over one of these 2 pi to the d epsilon m periodic cells, you can just compute it because we know what it is, right? So this is of size epsilon m minus 1 to the alpha minus 1. You may say, okay, but you know, is that big, is that small? Is it big or small? Sorry, alpha, sorry, alpha. Very important. Is that big or small?
Small.
It's small in absolute terms, but is it small in relative terms? In particular, is it small compared to this? And the answer is no. So this has size, well, it has the size that you get by differentiating this once, which is am epsilon m. And by definition, this number compared to this number is huge. So this is huge when compared to epsilon m to the alpha. So basically, we are not in the situation that we told you about because we have this constant background mean whose direction we cannot possibly guess. Of course, you're going to get unlucky and it's going to be maybe Diophantine. I mean, you don't know what the direction is. And what will happen is that before you have enough time to homogenize, averaging will happen. The trajectories are going to follow this mean flow, wrap around the torus before there's time to homogenize. So this whole story here, this needs a zero mean background. But a zero mean constant is the zero function, a zero background. Okay. So how can we get a zero background? And that's attempt 2. So I'm going to erase this, and I want to compare these two, what I'm about to write, to the old attempt. So this is attempt 1. And now let's do attempt 2. Okay, how do you make sure that something which is highly oscillatory views the mean flow in the background as not being there? Is you put yourself in the Lagrangian coordinates of that thing. Okay, so we introduce Lagrangian coordinates. So now you pick the time scale you want. So for all m greater 0, define tau m double prime to be 1 over the Lipschitz norm of the flow at level m, so epsilon m inverse. Okay, small constant, okay? Small constant times that, okay? And now define xml of t and x as the solutions of d by dt of x ml is um of t xml and xml at time L times this, comma x is x. So you have these Lagrangian flows and you seed them at these specific times. So you take the interval 0 to 1 or whichever interval you want, you break it down into pieces of size tau m double prime, and you know from ODE Cauchy-Lipschitz theory that you can solve within every single one of those time intervals the ODE flow very accurately. You know, the deformation gradient x does from being the identity can be made as small as you want by picking this as small as you want. Okay, so you introduce these. You also need the inverse flows, so denote inverse flow with an inverse. And now go back to this attempt and change it. So you still want to define a stream function increment you still have that sum, but now you need another sum over this L here, okay? You have your old partition of unity. So this has to do with switching of the direction of shearing. And now we have a different partition of unity. Let me just call it xi hat, which has to do with the switching of flow maps. Okay? And now, instead of putting this in Eulerian coordinates, you put it in Lagrangian coordinates. So you write times am epsilon m squared, same psi kappa, psi k, but it's xml inverse of tx over, and just let me fix something. This is not correct, what I wrote. You don't want to do this, because this way you're just constructing the flow at level m with the particle trajectories at level m. That doesn't make sense. You need the old ones, right? So you need m minus 1 here, and m minus 1. Now it's correct. So now you have the old flows. This is going to ensure that the background velocity um minus 1 is a constant as seen by an object sitting in here. And you have this time scale associated to this flow. And essentially, this is the vector field, right, Scott? I mean, I think it's a bit more subtle because of this partition. This is not actually a partition of unity. It's close to 1. It's a little bit subtle, but it's essentially it, okay? So this is essentially the construction of the vector field. And now you just iterate in M. Okay, so question. I've just defined a new vector field. Let's go back to the old problem. Can one prove this? Well, to see if you can, you need to check a couple things. Because remember, everything was predicated on having enough space. And the old constraints of having enough space said that the x scale separation satisfied this, and these fake switching times satisfied this. But now these times are not fake. These times you cannot remove in 3D either. Even if you have pipes or Mikados, you can't get rid of those, right? So what is the constraint they impose? Well, one is written on the board. And is there another constraint? Yes, there is another one. Namely, by introducing these Lagrangian flows, you don't want to destroy the Taylor diffusion process. What does that mean? You still want to allow these times to happen. So the flows have to be switched on a much larger time scale than the time scale of the flow switches, of the shear switches. Let me say that again. The flow switches have to be much slower than the shear switches, okay? And that means just that this is longer. It doesn't mean more than that. Okay? So now let's put these three things together. What are the three things? This one, and this one.
I think somebody needs to be MI for another way from your perspective.
Yes.
That double promise is MI.
Thank you, Scott. This is m minus 1 and that is m. Thank you. Okay. Let's put those three things together. So you need, what is the biggest constraint? So you need a m minus 1 inverse to be bigger than tau m minus 1 double prime, to be bigger than tau m, which needs to be bigger than am inverse am inverse times okay, so can you choose these times? Well, you can choose them if there is space. If this is much bigger than this, you can obviously then pick the times. If there is no space, you cannot do it. If there is space, you can do it. So what does that mean? am minus 1 inverse, this is also known as, did I write it anywhere? Epsilon m minus 1 to the alpha minus 1, I think, or 1 minus alpha, 1 minus alpha. And this thing is basically, did I write it? Yes, here, a epsilon m squared divided by kappa m, but kappa m is this. So is this much larger than this? Well, let's put them in the same denominator. This is and so the condition, these are small numbers, so this is bigger than this number if this exponent is bigger than that exponent. So need well, strictly less. But gamma was something explicit. It was not a random thing, right? Gamma is this. Okay? It's not a random parameter. Okay, plug it in, do the algebra, and you get that this is equivalent to alpha less and remember Q has to be chosen like this. So Q is super close to 1. So this means, but strictly larger than 1, but super close to 1. So this means that you can only do alphas which are strictly less than a third, but arbitrarily close to a third than you want. You just cannot do it otherwise. And this is why Scott and I stated that conjecture at the end of the first lecture. It seems that if you want to homogenize and increase diffusion, and if you want small scale features to be advected by the mean flow, you just end up with a third. We haven't used anything else. There's no Euler equation here. You just end up with a third. And that's it. So now, just give me 1 second, and Scott will say, I hope, a few words at least about, this is basically the super easy part of the proof, which is why I'm presenting it. And this is the super hard part. And I hope, so now this is a theorem for this construction, and maybe Scott in the last lecture will say a few words about how you would attempt to do this. I don't think he will try to give the proof, because it's ungodly, but some ideas about how you would prove this using a 2-scale expansion in homogenization. And let me end for now. Yeah.
Thank you.